Okay, let's just jump right in. Welcome back to The Explainer. Today, we're diving into some fascinating new research by Noah M. Kenny that basically turns abstract AI ethics into a very strict, almost ruthless mathematical balancing act. For years now, we've been debating how to make AI behave better, right? We want it to be fair, we want it to protect our privacy, we want to know exactly how it makes decisions, and obviously, we want it to be highly accurate. But what actually happens when you try to code all of those demands into a single system? Well, it turns out you hit a massive mathematical wall. And that brings us to the million-dollar question for today's explainer. Can an AI system actually be perfectly accurate, totally fair, completely private, and perfectly explainable, all at the exact same time? Regulators across the globe are demanding AI systems that do it all. They're basically asking for a unicorn. But as we're going to see today, the math tells a very uncompromising story. You literally cannot have your cake and eat it too. So consider this ultimate regulatory AI wish list. Huge frameworks like the EU AI Act, the GDPR, they all demand these four key pillars. We want high accuracy, because if the model isn't predictive, it's useless. We want exact fairness, meaning absolutely zero demographic bias. We want strong differential privacy to lock down user data. And we want explainability, meaning the rules the AI uses have to be simple enough for human to actually read and understand. But here's the catch. In the real world of machine learning, these four properties are fundamentally at war with each other. Section 1. The trade-off problem. Let's look at how these mathematical conflicts actually play out. First up, we have what's known as the fairness collapse. Imagine you have a model where the absolute best way to predict an outcome is closely tied to some proxy for a protected group. If you force that model to be exactly fair, meaning zero statistical bias between groups, the math literally forces the model to look away from its most predictive signal. By artificially blinding the system to anything that correlates with that group, you are mathematically capping your accuracy. The model definitely becomes fairer, but it becomes demonstrably less correct. Right, so what about explainability? We all want to know why an AI made a specific decision, but that has a price tag too. In this research, explainability is measured by sparsity, meaning the model is only allowed to look at a very small number of features. Now, explainability is cheap if your data signal is super concentrated in just one or two variables. But if the predictive information is diffuse, spread out across thousands of tiny variables, forcing the model to rely on just a handful of simple rules is incredibly expensive to its accuracy. And finally, let's talk about privacy. Enforcing strong differential privacy basically means injecting statistical noise into your training data to hide individual users. But guess what? That noise physically misaligns the model from the true signal, which actively destroys its predictive power. This steep cost is exactly why product teams are increasingly relying on local PII scrubbing, literally removing the sensitive personally identifiable information before it ever reaches the model, just to avoid paying this massive mathematical penalty on accuracy. Section 2. The governance frontier. So, if we can't have it all, if fairness, explainability, and privacy are all actively attacking accuracy, how do we measure what we can actually have? This brings her to the core of Kenny's research, the governance frontier. Until now, researchers usually looked at these trade-offs in pairs, right? Like privacy versus accuracy. But the governance frontier unifies all these tensions into one single mathematical object. It gives us exact, undeniable exchange rates between our ethical goals. Just think of AI design as a fixed performance budget. It's like a pie chart representing the absolute limits of your model's capability. If you want to allocate a larger slice of that pie to privacy or a larger slice to fairness, you mathematically have to shrink the slice that's left over for accuracy. There is no escaping this geometry. You are quite literally spending your accuracy to buy ethics. By translating all of this math into exchange rates, we can see the exact penalties. Fairness introduces a constrained optimization misalignment, which is a fancy way of saying the model is forced away from its natural target. Explainability causes a sparsity factor loss because, again, you're blinding the model to complex patterns. And privacy introduces a noise-induced penalty, which scales as a constant, k, divided by epsilon squared. The truly brilliant part of this paper is proving that at a foundational level, these penalties stack up. They are additive. They just pile on top of each other, pulling the model further and further away from peak performance. Section 3. Optimizing the privacy budget. This is where things get really practical. Let's zero in on that privacy penalty for a second. This specific fraction, k over epsilon squared, represents the exact accuracy penalty of privacy. And what is just incredible here is that researchers proved this is a fundamental law of information. This isn't just a bug in some developer's code. No clever algorithm, no massive future tech breakthrough is ever going to escape this fundamental cost. It is the absolute floor of how much accuracy you have to lose to get a certain amount of privacy. Because that hard floor exists, we can actually treat this as an economics problem. The math lets us equate the benefit of slightly better accuracy against the societal harm of slightly less privacy. We're looking for that perfect equilibrium. And this is a massive debate right now, because there is this huge gap between what everyday users expect for their privacy and what frontier LLM developers are actually contractually committing to. Finding that balance gives us this beautiful formula for the welfare optimal privacy budget, epsilon star. Think about the reality right now. 6 of the top frontier developers train on user data by default. And if you want out, those opt-out mechanisms are buried deep in incredibly dense legal policies. The governance frontier demands an actual privacy budget for higher accuracy. Instead of the Wild West, this formula gives regulators a hard mathematical baseline to hold companies accountable. Let's break down what this formula actually prescribes, because it's super intuitive. First, harder, high-dimensional problems rationally demand that you spend more of your privacy budget because the accuracy penalty is just way steeper. Second, if you have massive amounts of data or a really strong signal, you can afford to spend less budget, meaning you can afford to be more private. And finally, there's a variable in there for society's valuation of privacy. If a society decides privacy is incredibly important, the optimal budget mathematically drops. It proves that privacy isn't some one-size-fits-all rule. It scales directly with the mathematical difficulty of the problem. Section 4. Math meets policy. So how does this actually work in the real world? The paper highlights this concept from social science called commensuration. It's basically the transformation of different qualitative public values, like fairness and privacy, into a shared quantitative metric. The governance frontier is this incredibly powerful act of commensuration. It takes these vague, totally incommensurable values and makes them legible. It gives us a common currency so we can actually debate AI ethics using hard numbers. But, and this is absolutely crucial, we have to remember that pricing privacy against fairness doesn't magically make the hard choices for us. The math organizes a value conflict. It does not dissolve it. It just translates our moral dilemmas into data. It tells us exactly what our choices will cost, but it cannot tell us which choice to make. The ultimate goal of this framework is profound. To quote the paper, instead of burying value judgments inside model weights, the frontier localizes them into interpretable quantities that can become explicit objects of democratic contest. By pulling all this opaque technical discretion out of the shadows, a legislature or a community can argue over explicit value weights rather than unreadable code. We can debate the numbers on a dashboard rather than just blindly trusting an engineer's black box.
And that leaves us with the ultimate question, doesn't it? The one thing the math simply cannot answer. Now that we have the ultimate calculator to perfectly balance these metrics, whose morals are we going to use to do the math? When it's your personal data on the line, who gets to decide the acceptable cost of fairness or the social value of your privacy? The math has given us the map, for sure, but it's completely up to us to decide where we're actually going.